Welcome to classes on organic chemistry. Today's class is class number 8, and today I have taken hydrocarbon and specific portion is conformation. The conformation was actually a part of GOC, General Organic Chemistry, though it is included in hydrocarbon first year. That's why I have taken especially conformation. So conformation seems to be a very simple one, but there is a lot of things to know. Now, first of all, let me define what is conformation. Conformation types of molecules adopted due to rotation of carbon-carbon single bond is called conformation. So it is seems to be very simple. The shapes of molecule adopted due to rotation of carbon-carbon single bond is called conformation. I will tell elaborate. Now, what is isomers? Conformational isomers. These are the due to due to spatial arrangement owing to rotation around carbon-carbon single bond. Due to rotation of carbon-carbon single bond, a lots of structures or spatial arrangement occurs, and all these different structures due to the difference in spatial arrangement in space due to carbon-carbon single bond are called conformational isomers. So first of all, you may think that carbon-carbon single bond, say one, this is carbon, this is another carbon, keeping one carbon fixed, if you rotate that carbon along with hydrogen, that carbon will give a lot of possibility of arrangement of hydrogen attached to that carbon, and that's why it seems that the number of arrangement of molecule in the space is infinite, but in practice, due to bond angle difference of 1 to 20 kilojoule per mole, it is restricted, not infinite. Now, before coming to conformational example, let me first make some difference. What is configuration? I think maximum of you may not know what is conformation and what is configuration. So from my definition, you have seen that conformation and configuration both are nothing but spatial arrangement. But in case of conformation, the spatial arrangement differs due to rotation of carbon-carbon bond. Am I right? It gives spatial arrangement in different manner. Am I right? So this is called conformation, and the isomers arising out of the difference in structure in space is called spatial isomers. Now what is configuration? It seems to be equal. No. Configuration is again difference in arrangement of atoms in the molecule. Configuration in arrangement of atoms or molecule that can be changed by breaking and forming of bond. Huge difference, breaking and forming. In case of conformation, the difference in spatial arrangement occurs due to the rotation of carbon-carbon single bond. But when configuration occurs, the difference in spatial arrangement occurs by breaking and forming of bonds. You can't easily understand this point. I am taking one example. Say CH3 Cl HC3H7. This is optically active compound. It is chiral carbon. 4 different atoms or groups are attached in it. It has the ability to rotate the plane polarized light in right or left. This has optical activity. When you will make to react potassium hydroxide aqueous, am I right? So this is nucleophile. The attack in such a way chlorine is replaced by OH. I am not showing the mechanism. It is SN1 mechanism. So you will get the answer in this way. OH and another OH to the left, C3H7. It is not a single answer that you will just replace Cl by OH, you will get this one. It will be the mixture of this. Once OH is towards right and others OH is towards left, or OH is above and others OH is below. Am I right? And this two has the different optical activity. It may rotate the plane polarized light towards right, and the same extent it will rotate the plane polarized light towards left. And if it rotates towards left, it will rotate towards right. It is mesomeric mixture, racemic mixture. Am I right? Now, if you now imagine the structure is changed to that by rotation, no, it is not possible. It has come through carbocation formation. When there is carbocation, this is +3, plus carbon C positive. When C3 is removed, it is carbocation, and that carbocation is C plus. It is sp hybridized. Sp is planar. Am I right? So when sp2 carbocation is planar in shape, nucleophile attack either towards right or towards left, or from above or from below. You are getting two products. So my intention is that at the first place you are breaking the bond, and the second place the possibility of getting the two structure in the space either from right OH or from left OH. So once you are breaking the bond, in other case you are forming the bond. So that's why it is RS notation or configuration. RS configuration. Am I right? So the configuration or the arrangement, difference in spatial arrangement of atoms, which can be changed by breaking and forming of bond. When carbocation formed, it is broken, and OH is entered either left or right, it is forming. So by breaking and forming, the bond is formed. It is called configuration. Very often you are mistaken. That's why I have explained the term configuration. So now let me explain some other confusing term very often you get in the chemistry, but maximum of you do not know. One is torsional strain. Torsional strain. Caused due to electron repulsion of one substituent at adjacent to bond electron repulsion of other substituent electron bond electron repulsion. Torsional strain is nothing but electronic repulsion of bonded atom. Here in carbon there is CH3, there is CH3. With carbon there are two substituents CH3, CH3 is there. So bond, when it is bonded, so when there is a repulsion between the electrons of bonded atom or molecule, so the repulsion, the strain arising due to bond electron repulsion of one substituent adjacent to bond electron repulsion of another substituent. So electronic repulsion give you the torsional strain. Why I am telling this thing, when you will be asked to arrange the stability of some of the conformation, then this thing will come in. That I have explained the term torsional strain. Now next one is bond strain. Bond strain. Due to deviation of bond angle from desired bond angle 109.28 minutes. When the bonds are arranged in 10928 degree in tetrahedral fashion, the bond angles are as far as possible apart from each other, and it's avoid the further repulsion of bond pair repulsion or other repulsion. So this is ideal bond angle where repulsion is minimum, that is desired angle. When there is a deviation from this bond angle, if the bond angle is deviated from this one, that deviation cause a strain, and that strain is called bond strain. Again, this bond strain is again important for the reason, say, it is here bond angle, inner bond angle, alpha is inner bond angle 60, it is 30, it is 108, it is 120. There is a formula, you can find out what is the deviation from this one, and finding this deviation we can understand the stability of a compound. Now out of bond strain we are getting the ideal, and from this we will find out deviation, or you can write 5, where alpha is inner bond angle of a cyclic compound or compound. So if you assume that alpha is equal to 60, inner bond angle 60, if you place this value, get the deviation as 22.4. Here you will get deviation is 4.9, 9.4. Here you will get deviation, in this case you will get 44. In this case you will get deviation minus something, you calculate yourself. So you see, smaller the bond angle, greater is the deviation. Greater is the deviation, lesser is the stability. So this is least stable. It will be highly reactive. From this, it is more stable. From this, it is more stable. From this, it is more stable. So greater is the deviation, lesser is the stability, more is the reactivity. So it is least stable in comparison to this. In comparison to these two, it is least stable. Deviation is more. Here deviation is again less than this. More than this. This is less stable. This one. So order of stability is like this. Sorry, order of stability. Yes, stability is like this. And reactivity will be reversed. It is instantly react because there is more strain. Bond strain is more. 60 degree, it is 90. A bit relaxed, it is 108. Further relaxed, it is 120. Further relaxed. Less is the inner angle, more is the energy, more is the unstability, more is the reactivity. Less is the bond angle, high is the energy, high is the reactivity, high is the instability. Am I right? So out of this, we can calculate from bond strain, the stability of a compound. Am I right? So now another one again is very important and maximum of you don't know. That is bond strain or angle strain. You can write as angle strain. And another is static. Very often you have got this term, static strain. This is caused due to approach of caused by atom or molecule when approaches very close. When atoms of molecules approach very close, due to bulkiness of this, there is a strain on the molecule, and that type of strain caused by the atoms of molecules when approaching very close to each other is called steric strain. Upon this steric strain or steric hindrance, we see there is a competition of SN1 versus E1. You will get it in second year, substitution versus elimination. So these are the some important additional informations I have explained. Torsional strain, angle strain, steric strain. Torsional strain is chiefly on electronic repulsion, electronic strain. Angle strain due to deviation of angle from the desert angle, and steric is due to bulkiness when the one atom or molecule approach through other. So due to the bulkiness of this group, there is a repulsion that is called steric strain. So this is when we think of conformation isomers, we first of all think this conformation of isomers was projected in two ways. One way is Short horse projection. Very often we are confused how the projection is done, how it happens. We will first take the example of ethane. Simple. What is ethane? Ethane is CH3. So how we can project it in terms of Shor's? In Shor's process, the projection is done in this way: carbon. This is front carbon, carbon 2. This is carbon 1, carbon that carbon is called front carbon, and that carbon is called rear carbon, far away carbon. So near carbon, far carbon, front carbon, far away carbon. This is front carbon. Front is left hand corner towards left below, and some tilted way we draw another carbon towards right, and that is represented far carbon. So this two carbon has three hydrogen we have attached in this way, but you cannot understand how this occurs, and that form is called staggered. We will explain it in detail a bit later. Mind that this carbon is staggered. Why it is staggered? Because these two carbon, for convenience of our study, we have separated in big distance, but it is not so in practical way. Am I right? When, how we can say it is staggered? Because this carbon has three carbons, three hydrogens, and these three hydrogens arranged in this fashion. Now you assume, when this, assume yourself, mentally assume this carbon is placed over this, you see that hydrogen is placing here against this, and that carbon is pointing towards this against this, and this carbon is pointing, when it is exactly placed upon this one, this is placing against this. So I have drawn in such a way, keeping these six. When I place this carbon, all the hydrogen is placed opposite to each other of the first carbon. Carbon 1 and carbon 2. When carbon 2 is placed over carbon 1, we see the hydrogen linked with carbon 2 is placed against hydrogen attached with carbon 1. So they are far apart from each one. All the hydrogen of carbon 2 is far apart from all the carbon of C1, of all the hydrogen of C1, and that has got the name staggered. It has, due to repulsion fact, torsional strain fact, or these facts, we see this has got less amount of energy and it is stable configuration. So we will do one thing again. We will keep this in the same position, and say, many of you can be confused with this one. I have kept this one as it is. Carbon 1 is at it, but I have changed. I have made rotation through this carbon. I have made some arrangement like this. Am I right? So now, how can I have I written this one? So you see, when, if you place this carbon 2 upon carbon 1, this carbon 2 upon carbon 1, that carbon hydrogen is that one is very close to this one. If placed here, that is very close to this one. Very close to this one. When carbon over this one, the hydrogen is exactly adjacent to this one. When you place this carbon here, that hydrogen comes over here, and it is more or less very close to this one. When you place this one, in other way you can arrange, whatever way arrange, you arrange in such a way that when you place carbon 2 upon carbon 1, all the hydrogen of carbon 2 will be more or less very close to the hydrogen of carbon 1, and that one is called eclipsed form of ethane. And due to, when it is, if you assume this carbon 2 is carbon 2 is placed over carbon 1, then all the hydrogen of carbon 2 is side by side of carbon 1, and that there occurs a great repulsion torsional strain, and due to this the stability of this structure is, projection is less. So staggered configuration of alkane is more stable than eclipsed configuration. So this is the representation of Shohor's in Shohor's projection. You can in the same way you can do this thing CH3 CH2 H2 CH3. Am I right? If you take butane here also carbon 1 and 2, you made this carbon 1. If you take the example of butane, here you write CH3 and here CH3. Carbon 1 has 2 hydrogen, carbon 1 has 2 hydrogen, and carbon 2 has 2 hydrogen. This is one structure. This is staggered form. And you change whatever way I have told, CH3 here and this CH3 here, you CH3 here and this CH3 here, write this structure, you will get eclipse structure. You can write butane in this way, targeting carbon 1 and carbon 2 like this. You will get again staggered butane and eclipsed butane. And again in this case, if you place this one, this is exactly the, if you place this one over this one, this carbon over this carbon, this methyl groups one is opposite to the other, it is staggered, there is torsional strain is less torsional strain, and hence due to this fact it has got more energy, less energy, and it is more stable than eclipse form. So this is very simple, the Shohor's projection alkane, and I have taken the example of ethane and I have taken the example of butane. Now a bit complexity you will get, you will face when we will talk about Newman projection. It is a bit tricky. Newman projection, Newman projection, Newman projection. Here one circle is behind the other. The near or front carbon is designated DESIG, designated by dot, and far carbon is by circle. Near carbon CH bond is from the center dot, and far carbon CH bond is around circumference. I am showing you practically, you can understand. Say ethane CH3 CH3. Let us represent it with the help of Newman projection formula. Now there is also two carbon, one carbon and two carbon. Say one carbon is near front carbon, this is rear carbon, far away carbon, far carbon. So near carbon is represented by a dot, and far carbon, that carbon 2, is by, am I right? So one dot is a circle. If you assume this is one carbon 1, and that circumference 2 is another carbon, it is represented by 2. So it has 3 hydrogen. So CH bond, CH3, CH, CH, CH. There are 3 CH bond, 3 CH. That 3 CH is from center. H, H, H. Am I right? And now this CH2, and that red circle is nothing but far carbon, and it is represented by carbon 2. It has also got 3 CH bond. So one CH bond circumference, that is H, that is H, and that is H. So this is carbon 1, and that is whole circumference red one is carbon 2. So carbon 1 and carbon 2. This is Newman projection. This is near carbon, this is far carbon. It has got hydrogen, 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 CH3, and this carbon circumference red carbon is far carbon. It is called hydrogen, hydrogen. I have placed that carbon hydrogen bond in such a way that this carbon C1 is exactly over the carbon C2 is exactly above the carbon 1. In this way, one is above other. So when you place the other, in earlier cases in Newman projection we have seen, if you place in this way, so that carbon has this hydrogen, the second carbon has hydrogen, 3 hydrogen. If you place this one, so carbon hydrogen is exactly the in opposite direction of the carbon attached with first carbon. So it is staggered, it is more stable, it is staggered. Now we can draw a lot of other structures out of this. Fixing this 3, we have to keep fix 1, am I right? The carbon 1 fix. Now rotate that carbon, second carbon, rotate, make rotation. So we can rotate it in different angle, am I right? Except a bond angle difference 1 to 20 kilo per joule per mole, we can make a lot of rotation. So if the rotation is made in this way, say we have made a rotation like this 60 degree, am I right? This will come over this one, 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 am I right? A lot of other possibilities are there, I will show you a bit later on. But when I make a rotation of this one, carbon 2, that hydrogen will also rotate in this way. The configuration, the conformation where we get two, this is called eclipsed. So staggered ethane in Newman projection again is more stable energetically than eclipsed form. Am I right? Lot of other configurations are there. I am coming bit by bit. Now you follow. When we can rotate the carbon to 0 degree, 60 degree, 120, 120, 40, like this, 360. A lot of possibilities are there. Carbon 2 we can rotate 60, 60, 60, 60. Am I right? So out of this rotation we will get staggered, very important thing, minutely follow, staggered. Again in staggered there are something more. Staggered may be anti-staggered and maybe Gauche staggered. We will get 3 structure, we will show you later on. Then we will get eclipsed. We will get fully eclipsed, partially eclipsed. Am I right? So we have got staggered. No doubt out of this staggered, we will explain it later on. We will get anti-staggered and Gauche form, and in eclipsed we will get total or fully eclipsed or partially eclipsed. So we have got staggered, eclipsed. So other one left remain which has no mention. You don't know, perhaps it is not given in your book. I think it is given, just information is given, nothing explanation is given more on this one. It is the confirmation which is besides this. Out of this, if 0, 60, 1, 20, 24, 24 like this, multiple of 60, 60 if you do, you will get all this staggered and eclipse like anti-Gauche, fully partial eclipse like this. So besides these angles, if you made another rotation and if you get the confirmation on the spatial arrangement of atoms except rotation through this angle, all other confirmation besides the rotation through this angle are called skew confirmation. So largely we are getting staggered, eclipsed, skew. In staggered you are getting anti and Gauche, and in eclipse you are getting fully eclipsed and partially eclipsed. So we will make a summary upon this regarding the energy, how energy varies upon this one. So before coming to the energy, let us explain what is actually staggered and what are other part of anti and Gauche. We can show it distinctly with this ethane. Well, let us take the example of butane. With the help of butane, we will explain this. So So we have taken carbon 1 and carbon 2. Carbon 1 is in the center is carbon 1 and carbon 2 is the circle, where we are CH3 side by side, H and H side by side, H and H are side by side. So we have assumed as total eclipsed. We have assumed. Let us see what's happened. When this is made 360, from this part to this part is 120. That angle is actually 120. Carbon CH3 is 120, 120, it is 360, and this part 120, this part 120, this part 120. So one part you are getting 120. If you make 60, by assumption out of this one you are get 260. This is 20, here you are getting 260. So if it is here, making this towards right, this will exactly come in this position. So you are getting half of this one is 120 is 60. If you make 60-degree rotation, so you are getting this CH3 is exactly here, and that is here. Am I right? That is here. That will exactly come here. Am I right? This is one arrangement. Again you make another 60 means 120, another 60. This will this one. This will come here. This will go there. and this will come here, this will go there, and this will go there. Am I right? Now if you make again 60, this from it will come here exactly, from this it will come exactly opposite, and from here it will get come exactly opposite. If you make again 60, you will get these three are always fixed. Middle one, carbon 1 is always fixed. That is coming here, and that is here, and that is here. Carbon 2 out of the circumference, outside the point, that is from carbon 2. Now if you make this hydrogen CH3 of first carbon is again fixed. If you now make another 60, from this position it will come exactly here, CH3, and this will exactly here, CH3, and this will come here. So out of this configuration, you see, when this carbon 2 is side by side, it is totally eclipsed. Am I right? And hydrogen side by side. Now in this position, it is staggered form, but opposite to this one, but this all are edge of carbon 2 opposite edge of H, but all are opposite to each other, but these two groups are side by side, so it is Gaussian, but Gaussian staggered. Am I right? Again it is eclipsed, but it is total eclipsed because groups are side by side, but groups are not side by side. One bigger and smaller group. Again it is eclipsed. It is total eclipsed. It is partially eclipsed. Now again it is again Gaussian. These two groups are same. Again here you are getting hydrogen CH3, and when you make this one, this will go here, this is here, and this is here. So out of this we have seen total eclipsed, partially eclipsed, because here total eclipsed to CH3 group are side by side, and partially eclipsed one bigger group and another smaller is side by side, and this is totally staggered. It is anti-staggered. You can write anti-staggered, and this is partially eclipsed like this. So due to this rotation, we can get the Newman projection like this. Now if you now think about the stability, which is very often asked in exam, we can write anti-staggered or staggered is highly stable, then skew or Gucciform, partially eclipse, fully eclipsed, fully eclipsed. This is the stability of conformation of butane if you assume in this way. Okay, it has got less energy, it has got highest energy. Less energy is the most stable, highest energy is the least stable. Now, let me explain another important thing on which a question very often asked in the exam. Say, showing you it is a configurations of Newman projections of ethane, and its bonding is 120 of carbon 1, it is carbon 2, it is bonding only 20. So when is staggered, dihedral angle, dihedral angle, it is the angle between hydrogen of 2 carbon, between hydrogen of 2 carbon, it is dihedral angle. Between hydrogen of 2 carbon, the angle is called dihedral angle. So that dihedral angle for staggered configuration is 60 degree. Dihedral angle for eclipsed is, it is close to each other, close to each other, close to each other. So if these are very close to each other, so dihedral angle is, for eclipsed it is 0. A question very often asked, what is the dihedral angle in case of skew configuration? So if it is carbon 1 and if it is carbon 2, that 2 bond angle is equal to 29 degree. So if it is 120, so in case of skew, dihedral angle is 120 plus 29 is equal to 149. Very often asked in JEE in other tough exam, dihedral angle. So you keep it in your mind. For staggered HCH bond angle is 60. For eclipsed, it is HCH angle is 0, and for skew it is 120 plus this 29, it is 149. Till at all, lot of things remain untouched, and since the topic is a bit small one, so I don't want to make the class lengthy one. Thank you for watching the class. Hope you have find the class interesting.